Hello everyone and welcome to this my video on linear modeling, part of the mathematical methods course, well, units 1 and 2 at least. My name is Darren from Maths Guru. You're what? Maths Guru, my little corner of the interweb where all of these videos, downloadable lesson notes, VCEA exam questions and so much more are awaiting your free sign up. Yes, indeed, I'm doing what I can to try and help you smash methods. Now, our learning objectives behind me: be able to apply the knowledge from previous lessons to real world models relating to linear relationships. And as I say, if we look at the recap, we've done an incredible amount of work in this chapter already, looking at distance and midpoints and gradients and straight lines, equations with straight lines, graphing straight lines, etc. Now, what we've got to realize is that the theory behind all of this underpins real world examples, and methods is all about the real world examples. Can you extract relevant information from a question and turn it into undoubtedly an equation, and then either sketch it or find crossing points or x-axis intercepts, y-axis intercepts, all these various things to try and help us sort of model those real life things out there. All right, so that's our recap. Basically, as I say, there are two examples in this whole video. It's not going to be very long. If you can do me a favor, though, before I start, and that's subscribe to my YouTube channel, that would be massive. It sort of just says, hey, dude, yeah, we're supporting you. It also lets me know that someone's actually watching this stuff and I'm not talking to myself like a lunatic. So if you can subscribe and leave a comment if it's any good and all that type of stuff, that would be great. A historic site charges a tour company for priority entrance to the site. The charge consists of a monthly fee of $200 plus $3.50 for each tourist brought to the site. Construct a cost function. Well, a cost function basically is a formula that just starts with C, because that's how much it's going to cost. Function that describes the monthly charge and sketch the linear graph of this. Okay, construct a cost function. Now that's interesting because if you've ever taken a taxi cab in Melbourne or throughout the world, you'll notice as soon as you sit down, what do? They charge you a fee. Theoretically, you could get in the cab, shut the door, sit down, change your mind, get out of the cab again, and they're still going to charge you that flat for that sort of fee for just saying hi. And that's very much like a fixed cost. And in this situation, regardless of how many visitors there are to this tourist, yeah, it's going to cost $200. So that $200 is my fixed fee. Then it's going to cost $3.50 for every tourist brought to the site. Well, if we say let n equals the number of tourists, then we get the fact that we're going to take those number of tourists and times it by 3.5. Now again, whether we write the formula that way around or this way around, 3.5n plus 200 is irrelevant. The point of it is that is my cost function. Relatively simple, yes? Now, it says sketch the linear graph for this. Now, there would be an overwhelming need, I think, if I do this. And remember, whenever you draw a graph, you've got to do your axes and you've got to put your labels and you've got to draw it in pencil. Oh, we get very upset when you don't draw things in pencil. Basically, the overriding what is it I'm trying to say? The overriding desire from you guys will be to do this. You're going to put a cross here at 200, and you're going to basically do one of two things. You're going to draw a straight line like that. Yep. And then you're going to turn around and go, well, that's it. We could put another value on there if we wanted to. We could turn around and say, well, after 100 customers, put 0 there. Let's put 0 there. 100 customers is going to add another $350 onto that. And then 200 on that is going to be 550. So I could put a cross there and I could put 550 here. And we could marry on a little way. That's only one thing we could do, but there is a small problem here. And that is that there is no way we could join that line together. It should be discrete points. Now, the reason being is I cannot, my value of n here cannot take decimal values. It's not continuous. It is discrete. And as such, the chances are probably that line shouldn't be there. He says, trying to rub it all out. It should be just a load of crosses, yeah? Now, the other mistake I see people make, sadly, is they do this. All right? They'll draw some sort of line and ignoring that it's a wobble. The thing here that really throws people and gets, the examiner's pretty upset is putting in parts of the graph that simply cannot exist. There is no way that this part of the graph would exist because that would suggest there were negative numbers of people going to the tourist site. Simply not possible. So whenever you do these type of graphs, please, please, please take great care to make sure that you only draw the part of the graph that makes sense in a real world situation. And always, always, always second guess anything that might be on a negative axis. Negative volume, for example, doesn't make any sense. Negative time doesn't make any sense. All right, moving on to example 2. A car starts from point A on a highway 10 kilometers past the Wangaratta post office. I don't know why I said Wangaratta. Anyway, the car starts at a constant speed. The car travels at a constant speed of 90 kilometers per hour towards a picnic stop at B. Okay. So here is a line. Here is A, which is 10 kilometers past Wangaratta. There's Wangaratta. I know that's 10 kilometers. The car travels at a constant speed, so we're going that way at 90 kilometers per hour. And towards picnic stop at B, which is 120 kilometers on further from point A. So we now know that that distance there is 120 kilometers. Now, I always draw diagrams because my maths teacher said, Darren, a diagram is worth 1,000 words, which makes me wonder why I had to write all those essays rather than just drawing a picture. But moving on. And let t be the time, let t hours. We've got to make sure that t is in hours. Units become really important after the car leaves point A. Okay. I think I've got all the information there. A. Find an expression for the distance of the car from the post office at time t hours. Okay. So the distance, let's call it, what is it, D1, is going to be, well, it already starts. So this is the car from the post office is already 10 kilometers past Wangaratta. So that's going to be my fixed sort of unit or whatever it is. It's my fixed, what is it called? Fixed cost or fixed price or fixed whatever. And what is it saying? It is traveling at a constant speed at 90 kilometers per hour. That means it can do 90 kilometers in every hour. So that means I can work out 90 times by t. Because basically for every hour, for every variable t, for every increase in t, I'm going to do another 90 kilometers. Oh, that's it. Fair income. Part B. Find an expression for the distance d2 of the car from point B at time t hours. Well, we know it starts at 120 kilometers away. And then every single sort of time, every hour, it's going to get 90 kilometers closer. So in which case, I'm just simply going to subtract 90t from there. On a separate set of axes, sketch the graphs of D1 and D2 and state the gradient of each graph. Okie dokie, well, we can do that. So let's do D1. So let's do, what's that going to be, D1 against T. It's going to start at 10. So it's going to go here, and then it's going to go to some sort of value later. Up here, it's going to be a straight line. All right, so there we go. So what we can now do is say, well, let t be, oh, I don't know, 3, maybe. So let's have t equals 3. So we got 90. Well, actually, it doesn't make a huge amount of sense because he's trying to get to the post office. He's trying to get to B. What's a B? Stop B, which is 120 kilometers away. So the question is, if he's doing 90 kilometers an hour, how long is it going to take him to do that 120 kilometers? Well, I can do 120 divided by 90. Those zeros cancel, which basically gives me 4 on 3. So actually, he's going to, in 4 1/3 of an hour, get to point B. So I'm going to put a comma there, or sorry, I'm going to put a comma there, 4/3 comma. And we know that it is going to be 130. Now, why is it going to be 130, not 120? Well, he started 10 kilometers away. And if all else fails, put a value in there of 4/3 and you'll get 130. So that's the first thing. And I've got to write down the gradient is going to equal to 90. How do we know that straight away? Well, again, we know that this here is effectively in the format of y equals mx plus c. And what is the value of m? The gradient. And so in this situation, my gradient is going to be 90. Running out of room, he said, quite depressingly. There we go. So that now is going to be D2. That one there is going to be what? T again. So now I'm going to start up here at 120. I'm going to draw a straight line down. Although my GoodNotes thinks that I want to draw a curve. That's how bad my line is. There we go. Draw a straight line down. Basically, can I just leave it hanging there? Well, no, because we actually know that in this situation, we're actually going to reach my point. So I'm going to connect that to my line here. And what have we got here? We know that that's 0 and that's 0. We know that time is going to be 4/3. And in which case, we are done for that graph there. What is my gradient? My gradient is equal to -90. Believe it or not, that's the end. Hopefully that has been useful. There's no way I could cover sort of, every type of linear modeling equation I can, but that's sort of a flavor to get you going. Make mistakes, ask for help if you need to. But I'm going to move on to another video now. So thank you very much for watching. Hopefully it has been useful. If you can leave me a like and a subscribe, that would be awesome. Tell your mates and your teachers would be even better. But for now, take care, guys, and I'll see you again soon. Bye-bye.